A finite state machine is fully determined by its two truth tables, one that specifies the next state logic and one that specifies the output logic. We have here a finite state machine, and we'll see how we can draw the truth tables corresponding to the next state logic and the output logic. Let's start with the output logic. So we want a truth table that captures our output logic, and the input to our output logic is the current state. So here, well, we can't write A, B, and C for the current state, so we need to know the state representation. So someone needs to have told us how we represent state A, how we represent state B, how we represent state C. Let's say we're using one hot encoding, so A will be 0, 0, 1, B will be 0, 1, 0, and C will be 1, 0, 0. Now for our output logic, I need to write out a truth table, so it's going to be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. I've included all the possible states because I might be in an error state somehow by a cosmic ray. I guess I could have taken a shortcut and just used some X's in there. I'll do that presently. And why 3 bits? Well, we see that because our state representation uses 3 bits, then our output logic is going to depend on the 3 bits representing our state. So we simply go through. If I'm in state A, the output's a 0. State A is 0, 0, 1. So if I'm in state A, then I write down here that the output is a 0. If I'm in state B, so that's going to be 0, 1, 0 in my truth table, the output's going to be a 1. And if I'm in state C, which is 1, 0, 0, the output's going to be a 0. As for the rest, well, that just depends what we do if there's a fault condition. We could put question marks here if it doesn't matter. We could put a specific 0 or 1. It might be, for example, our finite state machine is controlling the brakes, and so as fail-safe we want the output to be 1 if there's an error condition, so it depends on the application. I guess we could have written the same output truth table in condensed form using 0, 0, 1, 0, 1, 0, 1, 0, 0, and then some way like just writing the word default like we would do in Verilog to indicate what we do if it's none of the above. This then of course gets filled out as 0, 1, 0, and then for default that depends on the actual application. The next state logic is handled in a very similar way. I'll take the shortcut way. So we've got our current state and we have our next state. The current state can be 0, 0, 1, 0, 1, 0, 1, 0, 0, and everything else. So I'll just write default here. If the current state 0, 0, 1, then from our state representation, that means I'm in state A. Then to compute the next state, I also need to know the input. So I can add an extra column here for the input in. For state 0, 0, 1, I can either have an input of 0 or 1 here. Hasn't been labeled yet. Let me make this 0. Let me make the blue ones a 1. So the input can either be a 0 or a 1. Same if I'm in this state, 0, 1. Same if I'm in this state, 0, 1. And with default, well, it could be a default here too. So default. If you prefer, I can just double everything over here so that I have a normal truth table. And then, same as before, we simply have a look. If the input is a 0 and the current state is state A, then the next state is going to be state B, and state B is 0, 1, 0. So I simply write in here 0, 1, 0. If the input were a 1 and I'm in state A, then my next state is going to be state A as well, which is 0, 0, 1. So I write over here 0, 0, 1. And then we repeat 4 more times. If I'm in state B and the input's a 0, I go to state C, and state C is a 1, 0, 0. 1, 0, 0. If I'm in state B and the input's a 1, I go to state A, which is 0, 0, 1. If I'm in state C and the input's a 0, I stay in state C, so 1, 0, 0. And if I'm in state C and the input's a 1, I move to state B, which is 0, 1, 0. And as for the default, well, who knows? Maybe we want to go back to state A, so we put in 0, 0, 1 here if we want to return to A. And that's it. Apart from these error conditions here, once we know the state diagram, then we can, and the state representation, then we can draw the output logic and the next state logic. In a more finite state machine, the output only depends on the current state. If it was a merely finite state machine, we'd have to add an input here as well. The next state depends on both the current state and the input, and it tells us with this combination of input and current state what the next state's going to be. The truth tables depend on the state representation, and as we saw in an earlier video, if we change the state representation, then the left-hand sides of these truth tables are going to change. And it's conceivable that some truth tables are much easier to implement than other truth tables. So changing the state representation can change the complexity of the combinational logic needed to implement our finite state machine.